All right. Lesson 2 in a unit on applications of the derivative, which really are more like consequences of the derivative. And today I want to deal with one of the biggest consequences of the derivative, and that's this thing called the mean value theorem. And before I can get to the mean value theorem, I've got to deal with a friend of mine. I've got to deal with Michel Rolle, R-O-L-L-E. Michel Rolle lived 1652 to 1719. Oddly enough, this is the only theorem he's known for years and years later. Curiously, he didn't like calculus, distrusted it, didn't think it was legit, and spent a lot of his career trying to discredit it. And so the fact that his name pops up in calculus textbooks just goes to show you how history sometimes doesn't give a rip about what you think. Rolle's theorem. Rolle's theorem says the following. It says assume that f of x is continuous on some closed interval ab and differentiable on some open interval AB. So it's continuous. I can draw the function without picking up my pencil. And it's differentiable, which means that it's smooth. No cusps, no corners. Tangent lines can be drawn everywhere. If f of A equals f of B, then there exists a C between A and B so that f prime of C is 0. That is to say, if we have a continuous differentiable function on a closed interval, there has got to be, oh, that's terrible. That doesn't even satisfy the theorem. That doesn't even satisfy the theorem at all. I've got a continuous function on a closed interval. It's smooth. And f of A equals f of B. If that's the case, there's got to be some place in between, maybe more than one, where the tangent line is horizontal. That almost makes sense. I'm going to sketch a proof. It's an iffy proof. I'm going to sketch it. Not going to write with any rigor, but we'll talk it through. Well, really, I'll talk it through, and you'll listen, because you're not really talking. I mean, maybe you're talking, but if you're talking, you shouldn't be. So stop. Proof. I'm going to play off the fact that f of x is continuous. If f of x is continuous, then we learned in our last lesson that there is a max and a min on AB. That was part of the extreme value theorem, the idea that if I have a continuous function on a closed interval, it takes on a max or a min somewhere. There are two options for that. Option number one is that the max and the min happen at interior points. The other is that the max and the min both happen at endpoints. If the max or the min happens at an interior point, then I'm going to play off the fact that f of x is differentiable. If f of x is differentiable and I have a max or a min, then I know that the derivative at that place has to be 0. I know if I have a max or a min and the derivative exists, the derivative has to be 0. And so that's our place, guaranteed by Rolle's theorem. If, by contrast, the max and the min both happen at endpoints, then I play off the fact that f of A is the same thing as f of B. If f of A is f of B, and those are the max and the min, then every function value is whatever f of A and f of B is. Therefore, f of x is a constant function. And if f of x is a constant function, then f prime of everybody is 0. So no matter how you slice it, there is going to be a horizontal tangent line anytime you can draw a continuous differentiable function where the endpoints have the same y value. This almost makes sense. You should draw 12 examples to make sure you get that. Excellent. Speaking of an example, let's confirm Rolle's theorem with f of x equals x to the fourth minus x squared on negative 3 to 3. What do I mean by confirm? I want to find the values of c that satisfy the theorem. Clearly this function is continuous. Everybody say yes. Clearly this function is differentiable. Everybody say yes. And a little bit tougher to tell, but f of negative 3 is the same as f of 3, comes from the fact that the function I gave you is even. Thanks, Mr. Ritter, for an even function, which means that there has to be some value of c in between negative 3 and 3 such that f prime of x is 0. And that's going to be easier to find than you would think. You're going to get x equals 0, and you're going to get x equals plus or minus radical a half, all of which happen to lie between negative 3 and 3. And so we have 3 possible c values between negative 3 and 3. A small warning here. Rolle's theorem is an existence theorem. Doesn't tell us where the c is, just tells us that there is one. Doesn't tell us how many there are, just tells us there is at least one. It's somewhat useless in that regard, except that Rolle's theorem is the thing that leads directly to the mean value theorem, and the mean value theorem is a biggie. We're going to use it forever. And the mean value theorem goes something like this. If y equals f of x is continuous on the closed interval ab and differentiable on the open interval AB. Again, that means I can draw the function without picking my pencil up from the paper, and it's smooth. I can draw tangent lines everywhere. You can't see me making those arm motions. I am making arm motions that say it's smooth. Then there exists a C between A and B such that f prime of c is f of b minus f of a over b minus a. What in Sam Hill did he just write? Well, I got a continuous function on a closed interval. Continuous function on a closed interval. What is f of b minus f of a over b minus a? It is the slope of that secant line. It's the slope of the secant line that connects the endpoints. What is that? That is the slope of a tangent line. What the mean value theorem says, if my function is continuous and smooth, then there has to be at least one place where the tangent line and the secant line are parallel. Possibly more than one. Possibly more than one. But there has to be at least one place where the tangent line and the secant line are parallel. This is one of those things that almost makes sense if you think about it. Of course, this is school, so we don't think. But this is the thing, the slope of the tangent is an instantaneous rate of change. The slope of a secant is an average rate of change. So if you get on the thruway and you drive for 100 miles and it takes you 2 hours, then on average you were driving at 50 miles per hour. What the mean value theorem says is that at some point on that trip, you were going exactly 50 miles an hour. That's all that says. And that actually makes sense if you think about it. But again, this is school, so well, I mean, what are we going to do about that? By the way, the proof on this, I won't give it to you because it's a nasty proof. What we basically do is we define some new function. We define some new function h of x, and we let h of x be f of x minus the line, minus the blue line. Maybe I should color code that. f of x minus the blue line. And that h of x ends up satisfying Rolle's theorem because it's continuous, it's differentiable, and at both endpoints, h of x is 0. And so if we run Rolle's theorem on h of x, we get the mean value theorem. It's a really bizarre result. Not everything satisfies the mean value theorem. That doesn't. That doesn't. And that doesn't. You should pause and ask yourself, why do these not satisfy the mean value theorem let's pick an interval. Let's move everybody down and let's set our question specifically. Why do these not satisfy the mean value theorem on -1 to 1? What is wrong with each of these functions on -1 to 1? Well, at x equals 0, this one is not differentiable. And so if we're not differentiable, mean value theorem doesn't apply to us. And so there's no place where the tangent line is going to be parallel to that secant line, because if we were to try to draw a tangent line there, it wouldn't work. Similarly, for g of x, you've got this thing happening. What the heck is wrong with that? Oh yeah, this thing is not continuous at x equals 0. If you're not continuous, mean value theorem does not apply to you. And then h of x, don't even get me started on h of x. H of x, you've got this happening. We're continuous, but we're not differentiable at x equals 0. The mean value theorem requires continuity and differentiability to be used. Excellent. So what's it going to look like? Let f of x be x squared minus 3 on -1 to 2. Find the c that's guaranteed by the mean value theorem. And the mean value theorem says that there is some c, if we're continuous and differentiable on the interval, and I think we are, that's a polynomial, so polynomials are continuous and differentiable. Mean value theorem says that there is some point such that f prime of c is f of b minus f of a over b minus a. Well, f prime of x is 2x, so f prime of c is 2c. F of b, oh boy, that's 1. F of -1, f of -1 is -2 over 2 minus -1, so that's 1. And so the c value in question is 1/2. All mean value theorem problems have the same rhythm. We take a slope of a tangent, take a slope of a secant, and set them equal. Excellent. Slope of a tangent, slope of a secant, set them equal. Marvelous. When we come into class tomorrow, I've got a couple more just like this for you. Until that time, stay safe in internet land.